with the
I
fun
don't
one.
either.
Like, I don't even know what it,
I
like,
just get
you see
excited about
crushes
how many
it.
likes we have. Oh, let's see what we have now. I checked 5 minutes ago, but now.
But you never know. Austin, have you liked our page yet?
I have.
Okay, good.
Of course.
Yes.
Has everyone in this room liked the page? Just
Yes.
checking.
Okay, how many powertrain people today?
That's all.
Oh, Brock. 2 powertrain?
Small will be here.
Yeah.
Okay, 3 powertrain. How many suspension?
There's 3 of those.
3 suspension.
Yeah, one's missing.
And how many chassis?
Calling all chassis, we're all
Okay,
here.
so I'll try to focus on a little more on chassis. We're
Woohoo!
right.
I know.
This is the first.
So let's see. Last time
Just like,
we got
I don't want to
through
hear any things about me asking that question.
double A-arm analysis, looking at the online program, and then more sophisticated ones. The only follow-ups on that are, this is the free program to do double A-arm suspension design. It's called Wishbone EXE, and it's a old program, but it still runs on small program too. This is like the day of Windows 98.
Yeah.
Oh, hopefully you'll let me on this computer. It's not gonna like that. All right, so that went into some weird mode. No, it did work. Okay, so this one is 3-dimensional, X, Y, and Z. And so you can indeed look at things like bump steer. And let's see, so it's not as nice as like a new program where it's completely interactive. When you hit the calc button, you get a picture, and that's a static picture. So you have to go back and forth between, like, give it 2 inches of bump, calc, and then it'll change your picture here. But it does give you the important stuff, like, let's see, kingpin angle, trail right here. It gives you the instant center location. Those are nice. That's relative to the opposite wheel. The instant center for anti-squat, the percent anti-squat with inboard brakes or outboard brakes, scrub radius, Ackerman statically at least, and then you can figure it out dynamically with a bunch of changes. And you can do things like steer at a certain amount. I don't know what the units are, but so that's there, that's free. And there's another program that looks like it's free from Lotus Cars, and they have a program called, Lotus Suspension Analyzer. Apparently 1 academic seat is free for this thing. And it will do solid axle, so not much use to the rear of the Build a Sola project, but it will do double wishbone and semi-trailing arm. So that sounds like definitely worth looking into, see if we can get a seat. And if you want more than 1 seat, maybe we can pay for, it's probably a couple $100 to get a site license. And then lots of people can use it. So take a look at that site and email them to see if we can, what that's about. There are other programs that are typically about $300 to $700 for suspension analysis, but I'd say if that Lotus one looks like it'll do what we need, so go there. Okay. So a little bit on, I thought I'd start on, since we talked about suspension last time, let's wrap up with the rear suspension on semi-trailing arms, and then we can do powertrain and particularly chassis structure. Just try to spend most of our time on structure. Okay, semi-trailing arms. So this is one of the simplest rear suspensions that is also gives pretty good properties for things like your camber gain, your roll center, and bump steer. It's used on, let's see, the first car to use it might have been like the Porsche 911. I don't know if that's the first one, but the first popular car to use it, that perhaps, that was in the mid-60s. And Volkswagen Bugs then used it, Porsche 914 used it, BMW used it forever until, I don't know, some recently they switched to double A arm rear. But they use semi-trailing arms for a long, long time. And that's because it's pretty good. You know, for a simple suspension, it does things quite well, considering only one arm. One of the key parameters is the angle here. So what is it? Wheel, a single arm, 2 inner chassis pickup points. So that's why it's called a semi-trailing arm, because it doesn't trail directly backwards, it trails off at this angle. The purpose of this angle, in this case 24 degrees, is two purposes. One is to get the roll center off the ground. In a pure trailing arm, sorry, this is top view, that's the front of the car. If it was a pure trailing arm and the wheel was just directly back, pure trailing arm and the pivot would be there, then the wheel just moves this way. So it sits and considers infinity that way, and that means the roll center's on the ground, and that means you have more body roll, and generally not good. You also get no camber change with roll. Your wheels are always parallel to the car. So in a street car where you want that outside tire to ideally be negative camber, then a pure trailing arm will not give you that either. Now this will only make up some of it in a street car, but better than nothing. So the key number is that angle, because that angle combined with how far away the points are gives you your instant center. Now this is a little misleading. Unfortunately, they made the instant center point right at the other contact patch of the tire. That's totally arbitrary. Ignore this wheel. That point can be anywhere you want. If you put it real close, then you have equivalent of a swing axle. We're back to the old tuck under problem. So that's why you don't want it too close, and that's a pretty steep degree. Most of the cars are like 13 degrees, 20 degrees at most, I think. So this point's generally around here. Then that's telling you for lateral loads, cornering loads, where this line intersects that center line of tire, that's the equivalent instant center for lateral loads. Okay. So this picture now combines, this is the top view up here, this is the rear view of the car. In this case, we have both of those inner pivots at the same height, which is typical. And when you do that, your instant center is at that height. This is where you can see the instant center cross the center line. So first you find that intersection point, then you drop that down to your rear view at the height where it also intersects there. Then you draw a line from there to the contact patch. And if I were to do that for the left side of the car, the opposite wheel would have a line like that, and they would cross at the center line. That's why they haven't drawn the opposite wheel, because you don't really need to. You just need to know, where does this line cross the center line of the vehicle? That is your roll center height. So as long as we can get this point fairly high, then we're going to get a reasonably high roll center, and we'll have less body roll. And we don't want it too high so that we don't get jacking. So this one is 165 millimeters. So that would be about 6.5 inches or so, something like that. Okay. Stop me at any point if this isn't making sense. Oh, here's typical angles. Porsche 914, 16 degrees. BMW range between 13 and 20 degrees. For you, now they're trying to get probably more camber gain so that they can corner faster. In our case, we don't need a camber gain. In fact, we want the wheels for big bumps to stay relatively vertically. So that would argue to have a less of an angle, maybe the 13 or even less than that. On the other hand, we do want a fairly high roll center because our CG is way off the ground. So I don't know what the right answer is, but the way that I would find out is, a strategy to find out is to say, what is an acceptable jacking amount? And by amount, I mean distance. So we know whenever your roll center is off the ground, the car will jack. It's going to raise when you go around the corner. How much is okay? Some 1/10 of an inch, who cares, right? So 1 inch, 2 inches, now we're starting to care. So this is the constraint on how high your roll center can be. And we can go through it. It's not too hard to do. You don't have a spring. Just assume a wheel rate. Okay, wheel. And you know when you go around a corner, you have a certain amount of weight transfer, delta F, delta W. And that's going to be equal to M, A, H. H is that distance from the roll center height to the center of gravity divided by T. That's your weight transfer. A is probably around 0.6 Gs for an off-road car. The easy way to write that is not to find the slugs, but just to say the weight of the car times 0.6 times H over T. That's the total weight transfer that's going onto the outside wheels. Then you got a front wheel and a rear wheel that are taking all that weight transfer. Then you know that the front and rear wheel have a KW. You know that F equals KX. X equals F over K. So the F is the delta W, and the K is the K of both front and rear. You could split it up into just the rear and just the front, but the whole car is going to roll as a whole if it's reasonably stiff. So that'll give you a, let's see. Oh, no, wait. I'm confused. I'm calculating the roll angle. So sorry. This is another calculation. You need that. You need the delta W. Okay. Now that you have the delta W, now you can calculate how much cornering force we have that we can withstand on that by mu. So that's mu delta W. The roll center height is here, let's say. There's a theta here. We know that this delta F is transmitted along that line, and therefore it has a vertical component. And so this is the jacking force right here. So it's the vertical component, the delta F, when you put it into, let me draw a little triangle here. That's delta F equals mu delta W. This is jacking force, Fj, what do they call it? And this is that angle right there, geometry. So once you have your Fj, now you do what I started to do, that's why you're confused. You know that the suspension follows F equals Kx, therefore X equals F over K. the F is FJ, and the K is K wheel. And you have to keep your front and rear straight. Either do the whole car or just do the rear end in terms of your forces. That is if that's a 1/10 of an inch, we don't care. If that's 2 inches, we care.
Is that how much the whole car will jack, or how much the shock will absorb? Like the distance the shock will absorb?
That's how much the whole car moves.
Okay.
To go to the question of the shock, then we need to look at motion ratio.
Okay.
Yeah, but we don't have to look at motion ratio if for this level.
Yeah.
So you might, maybe one place to start would be, how much are we willing to let the car jack? I don't really know. But let's say a 1/2 inch, just for example. Start with that, 1/2 inch. You know your K wheels based on your corner weights and your wheel frequencies. That'll give you a jacking force. That'll give you this number. We know mu W. Now we have just inverse tangent of that over that. That'll give us our theta. Now that we got our theta, we know that the roll center has to be on that line, cross center line wheel, roll center height. Got your roll center height. Now go backwards. Keep projecting that roll center height so that this instant center location gives you it based on those locations. How many followed that? Okay.
I have a question.
Yeah.
So if you wanted to raise your roll center, looking at these two,
Yep.
you could increase that 24.25 angle, the angle of the semi-trailing arm,
Yeah.
so that that intersection is closer to the center of the vehicle, and that would raise the roll center.
That would. Yeah, that would give you more jacking. It would also, though, this is the unfortunate thing about semi-trailing arm, it gives you more camber gain. So your wheels are going to be going like that in big bumps. So that's the limitation of semi-trailing arm is we only have one arm and 2 points. Simple. We only have one arm and 2 points. We can only control 2 points to do what we want to do. And so there's always compromises. You're not going to get everything you want.
Go ahead.
So we want a little bit of camber gain though, right?
Probably, yeah.
Performing.
Probably, yeah.
Okay.
Yeah.
In the past, when we were looking at other suspension systems, we were hoping to get the instant centers outside of the tires.
Yeah.
Are we still aiming for that here, or is it less important for semi-trailing?
I think so. That I would, yeah. Mostly because if you got 10 inches of wheel travel, then we don't want those tires going way inboard.
Yeah.
We know when it rolls, it's only going to probably go 3 degrees. We did some calculations for that. So
Because if they're outside of the wheels, they travel linearly.
more linearly, yeah. So let me see where people got lost. How many accept that when you go around a corner with an independent rear suspension, the car will jack? Pretty much everyone, okay. And we can all accept a certain amount of jacking, 1/2 inch. So that's this number. This is the amount of, let's see, how many follow like this little triangle? Okay. How many buy the fact that when you put a lateral force on, it has to be directed upwards in the suspension? Not bad, okay. So I think we just got lost at the end.
Maybe we can explain the W a little bit more and how I went from MA to W.6.
Oh, yeah. So this is the lateral acceleration of the car as you're on the corner.
Yeah.
And so on a street car, that'd be like 0.9, off-road car 0.6. So if I go M.6 G, now I just group the M and the G to get W.
Gotcha.
They don't have to deal with slugs.
I'm just trying to visualize this so that drawing with the tires, if the front of the car is into the board, if the car's turning left.
Yep.
Okay.
Yeah, that's right. Yeah, so I always assume rear view and turn left, NASCAR. Or IndyCar, whatever you want. Okay.
Sorry, what was T?
T is track width. Yeah. So that gives you your weight transfer. And H is the distance between they called it B. So the roll center's there and the sprung mass CG is there. That's what I was calling H. That's the roll moment arm. Okay. Other questions on the board, and then we can go again through how we can get the roll center height.
So does the ride frequency, is that the same for the front and rear? Or is that
Close,
changed?
close. That was, it depends on your wheelbase and what your goals are.
Alright.
One approach, which is what street cars do, is, say, I briefly went over this before, but let's see where I put it. This document's getting so long, it's hard to navigate now. Ride frequencies. There it is. Okay. So I think I gave the example where you have your car. Let's say this is my car.
Right.
And it's traveling along. The front hits a bump. If you're driving the car, it's most comfortable if you have the rear frequency a little bit more than the front frequency. And here's why. You go along. If you have a soft front end and you hit the bump, it won't respond right away. It'll respond slowly. And so as the car is traveling, the rear hits the bump. If it's stiffer, it'll respond quickly. And so you can get the car to do that, and then it just settles down. If the front's too stiff, you come along, you hit the bump, it does that, and now you hit the rear bump, it does that, and you feel yourself do this. Yep. So that's for ride comfort. Is that what should govern a Baja car? In a 4-hour race, probably.
Because wouldn't that also help us determine what kind of shocks we want to use, like the spring?
Yes, that would tell you your that. So that analysis is in the Gillespie book, and there's some formulas for figuring out. So they're showing like this idea here, and it's probably in the Millikan book as well.
Okay.
So you would recommend having a stiffer rear shocks than the ones on front?
Yes, well, the fundamental thing is the frequency, the wheel frequency. And then, so if you have a 50-50 weight distribution, the rear springs will also be stiffer. And if you have a heavier rear end, then they're going to be stiffer by quite a lot.
Yeah.
Yeah. Because we need both stiffer for the more rear weight and stiffer for the vertical frequency. Okay. Let's see. So questions? Any other questions on the board work? Okay. So now let's look at how we finish it. So this gives us, what was the result of this? FJ theta. If you know your theta from this little force triangle, then that's the very same theta as this view, right there. That will give you geometrically your roll center height. It will also give you, oh wait a minute. This might be a guess. I think it's something, I've never actually designed one of these, so realizing the complexities. This line we will draw based on the theta. Then you go to your top view line, and why am I confused? Never a good sign on the personal team that's confused. So we know that when we did this one, it was not hard to figure this out. We know that we took this line, found out where it intersected the center line of the car, dropped that point down to here. Oh, we dropped it down to where it crosses, it looks like, oh, the inner points. Yes. Okay. So the height of the, now in this particular picture, and this is a little misleading, these points, the author put at the same height as the center line of the wheel. Totally arbitrary. these points can be anywhere. So you take this line, you draw it, then you take your chassis points, let's say they're up here, you draw that line where they intersect. That is the instance center for that wheel. Then you take that point, you go up. Let's say it's here, you draw a line up. Take a point where it intersects that center line there, and then draw that through your inner points in the top view. And that will give you this theta right here. That was a better explanation, I think. But not really. Okay.
It's one of those things you probably just have to do a few times.
Yeah,
before
yeah,
it makes sense.
yeah, okay. So, I mean,
Like
maybe
you have to do a personal practice.
we don't all have to know this. I think everyone needs to know, like the frame people, they're gonna be involved in those 2 points. So you're gonna be able to support those points. So you'll wanna know what's driving why is this chassis team trying to get them here? And this will help you understand that.
So, Professor,
Yeah.
so after raising it until it intersects with that line up there, the center line, is that the theta?
Yes, once you find this point,
Yeah.
where it intersects, then you draw, well, so then you have to make a decision based on your overall chassis, is where can I afford to put those points? So where do you think, what other factors would play into the location of those points?
Let's see, trains.
Drivetrain? Uh-huh. So we can't have if the engine wants to occupy that space, couldn't put it there.
What type of travel we're trying to do with the wheels? Like how long is the trailing arm?
Yeah, right. So if these points were like right here, that wheel is not going to go very far before it's going forward and backward. In other words, in the side view, there's the wheel. Your straight trailing arm points, let's say, are here. Oh, I've got a picture of this. Sorry. Here we go. So let's say the semi-trailing arm point was there in the side view. As the wheel goes up and down, it's of course going in a huge arc. And so when it's down here, that's not bad because the rear is going backwards. That's recession. That's generally good for a rear suspension. But as it goes into bump, that's going into precession, going forward, and that suspension will lock up when it hits the bump. So, interesting. In some ways that's good because the suspension gets stiffer as it goes into bump, so it will have less tendency to bottom out. On the other hand, you'd like the suspension to be very, let's say you have 10 inches wheel travel, you'd like it to be very supple through like the middle 8 inches of that travel. And only in the last inch do you want it to like progressively tighten up so that you don't slam into the bump stop. So I would argue that this is still not good. You probably want that point far out. So if we want a long side view instance center, then we're going to have to put these points that way. And so how do you find that point? That point is found by the intersection of this line and the center line of the wheel, right there. So the idea there is that forces are transmitted, longitudinal forces are transmitted through the contact patch right here. And so where does that force line cross the kinematic line? And that is where that effective axis point is.
So we're gonna wanna have trailing arms that are like at rest with the driver in the car that are like still drooping down a little bit, right?
Probably,
For the
yeah.
best absorption.
So that you can, that'll give you a little, well, you get some precession automatically actually at the contact patch. Well, actually, I have to think about this. Let's see. Is it the
I mean, if
contact
it's horizontal, then it's just like it's at
Yeah.
that point just
Yes,
moving vertically,
yes,
right?
yes, that's right. I think it is to the wheel center, but You know, I've done this in so many years, I've forgotten. So in the, right, so these 2 points probably want to be above the wheel center line. So we want these points to be long, we want the arm to be long. One of your constraints is going to be your wheelbase. So here's your car. You know that you don't want too long of a wheelbase because then you can't get around the maneuverability course. So if we know our L and our driver's feet are probably going to go like here, I'm just guessing, and then we need to package it for a driver of a certain size. So this is where the mannequin models in SolidWorks are going to be really handy. You can define the size of the person. You know your rear roll hoop is probably there. And I drove way too low, but oh well. So your suspension arms, maybe you can get them underneath, I'm not sure. But most designs I've seen are putting them right there or somewhere, around there. So the fore aft location is also going to be fixed by probably your rear roll hoop.
Do you know if that violates the rules or not?
What's
By
that?
chance, putting it on the roll hoop, because from what I understand about the roll hoop, you can't connect any member more than 5 inches away from the nodes on the roll hoop. So
Okay.
I only need to double check that, and that's actually what I'm looking for right now, but
So let's just have to see
I'm
what they mean by
unsure.
that. Yeah.
I'm unsure.
Connect this, like the side members, the side frame members to it.
Yeah, but they want it down low, like by the buns.
Yeah.
So, yeah, we're gonna have to look at that.
Yep, yep. Okay, so long arm is good on your semi-trailing arm. Let's see. Now there's also a effect of toe. These points here, I'm not sure I'm going to show this. Let's see if I can. Pretend this is my semi-trailing arm, and that I've got a wheel that's right here. So as this semi-trailing arm goes up, the steering of the wheel is changing. The toe, the way that the direction that the wheel is rolling or pointing is also changing. You see that? So that's another compromise, is that when we only have 2 points to control, we're going to have to give something up. It's not so bad though. If you do the normal way of them at the same height, then you get, let's see, you get a stable situation. That's a good picture. Okay, case, I think it's case 6, or 1, 7, and 8. So what is this graph? This is toe in on the here. So 0 degrees toe in is how we start. This is bump, and this is rebound. So this is the wheel going up into the car, and this is the wheel dropping. And if you have them at the same height, then you get toe in both directions. And that's a pretty good thing. For a rear suspension, let's see. The idea is when you go around a corner and you're loading that outside tire, if that right rear wheel toes out, you spin out. So you want it to toe in very slightly. The other situation is when you brake, the car pitches forward, the rear usually lifts up, unless you have a lot of anti-lift, and you might have a lot of anti-lift. In that situation, the rear wheels are drooping, and if they were to toe out, that's also unstable. So this gives you toe in both directions. So that's a good solution. People have played around with the heights to try to, let's see. So in this view, our heights were level, but you can see that if I were to drop one or raise one of them, I can also change my roll center. So here's, in the top view, this is just like before. So here's one where they have inclined the inner point down. And, oh, sorry, this one. This is the arm to look at. When you incline the inner point down, it drops the incident center. That drops the roll center. You could do the opposite and raise it. But the point is that when you raise or lower those points, you get a different toe curve. So 1, 7, 8, and 6, these are all symmetric cases. And then this 2 and 4, this is the toe curve for example, raising one of those points. And cases 3 and 5, that's the toe curve for raising the other point. I don't know which is which. You can look at it. But I don't know a lot about semi-trailing arms, but I think you're pretty safe just making it with the same height. It is pretty sensitive to the height. I think those, like in this case, those changes were only 20 millimeters difference in height, and you get a pretty drastically different toe curve. So when you build the frame and you build those points, you want to get those within a few millimeters of the same height. Okay. So semi-trailing arms. Any questions about those? Who's designed the rear suspension? All right. Okay. What do you think?
It'd be wild.
It is a good suspension, so you just have to understand it. All right.
We're kind of leaning toward a, the semi-trailing arm design without any, some of them have those lateral, kind of almost A-arm type members.